So for this talk, I will be talking about AI training, mixture of expert training. I'm Athinagoras, research scientist at NVIDIA. And this work has been done with many amazing collaborators while I was doing my PhD at Stanford, where I was advised by Christos Kozyrakis. So this talk in a nutshell, mixture of experts training is very hard. We have different experts with different amounts of load. If we want to optimize for convergence, we want to make sure that all experts process their full amount of load. But if we want to optimize for latency, we want to make sure that we load balance resource utilization across the system. And this has been a very difficult to tune trade-off between convergence and latency. I'm going to present SYMI to try to optimize for both simultaneously. The intuition behind our design is to decouple expert placement from their corresponding optimizer placement. And we'll present a system where we rebalance experts on every training iteration with very low overhead and are able to significantly accelerate training. So it's 2026. I don't need to persuade you that MOE is an important architecture. All the very large language models today use the MOE architecture or are rumored to use the MOE architecture. So how does it work? Let's take the transformer, for example. We have an attention component followed by a feed-forward component where the majority of the model parameters reside in. The mixture of expert architecture extends this by replicating the feed-forward component into different versions. We call each version an expert. And then a learned router routes every token to only a subset of those experts. And experts are trained independently. This setup case selection, for the context of this work, I'm using the case of k equals 1. So every token goes through exactly one expert. So the MOE architecture essentially extends the dense architecture with many experts, but only a subset of those are activated per token. And if we take a look at the dimensions of the core matrix multiplications per token, they're the same. So the compute requirements of the two models are very similar. But the MOE model has many more parameters. As a result, a much greater capacity to learn and is able to efficiently achieve better accuracy. Okay, so how do we deploy this? In modern systems, we have hundreds of experts. It will be extremely wasteful to place every expert in every GPU's memory. So we do expert parallelism. In expert parallelism, we place different experts in different devices. And to increase training throughput, we also use simultaneously expert data parallelism, where every expert class is replicated a constant number of instances. In this example, every expert has 4 instances. And in every training iteration, the input batch, which is partitioned across the resources in the system, every token is assigned to an expert. And we apply an all-to-all collective to route every token to a device with its corresponding expert. Now, here's the problem. It turns out that the expert popularity distribution, how many tokens each expert receives, is very skewed. So we have a big latency problem. We have to wait for the device that hosts the most popular experts to finish all their computation. And at the same time, the remaining system is kept idle. So one solution is to establish some expert capacity. This is the maximum tokens that every expert can process, and then we will drop the rest. And this greatly improves utilization and latency, but it significantly slows down convergence. In fact, the more token we drop, the worse the model quality in the system. So in MOE training, we have this very hard problem of balancing between convergence and latency. In practice, people use a combination of different load balancing losses. We have losses that penalize the router or the loss objective if the expert popularity distribution diverges from uniform. We have auxiliary losses that try to stabilize training on top of that, and every one of those losses comes with its tunable coefficient. Training is already a very hard problem with many hyperparameters to tune, and we shouldn't add more. And if we should any, these should be AI quality knobs, not system performance knobs. In an ideal world, we want to have good convergence, but don't have to worry about system performance and latency. So we'll start building our solution on top of the concept of adaptive expert replication. In an ideal world with adaptive expert replication, every expert, given some expert distribution popularity, is replicated adaptively and proportionally to this popularity. And it turns out that expert popularity is not only very skewed, it's also very dynamic. We have to rebalance experts every time this popularity shifts. So if we have this, where experts are replicated proportional to their popularity, we get great system utilization with very low token drops, and we get the best out of both worlds. But it is expensive to move experts. And to make things even worse, we don't have to only move the expert weights, we also have to move the giant corresponding optimizer that comes with every expert. In this example, I'm using FP16, FP32 mixed precision training with Adam. The optimizer state per parameter is 8 times more data compared to model weights. And today, people are using FP4 training with optimizer in FP16 or FP32. The ratio of state that resides in the optimizer per parameter is 16 to 32 times. So the overhead of migrating the optimizer is just too large. And let me now try to illustrate how bad this can be. In this figure, I have expert weights on the bottom and their corresponding optimizer on the top. With very large models, that the optimizer is very large, we have to shard the optimizer because we cannot accommodate it in the given memory. And it is standard practice in all implementations that we shard the corresponding optimizer of every expert uniformly across the nodes that host that expert. So here, expert 0 is somewhere node 0 and node 1. We split evenly the optimizer between those two nodes. Now, with adaptive expert replication, every time we have to rebalance experts, we have to reshard and migrate the optimizer accordingly. And because the expert popularity distribution is very dynamic, we have to do this very frequently. And this is a very big cost in terms of network communication that really increases the iteration latency. So at this point, I will present SYMI, our system that tries to achieve low overhead per iteration adaptive expert replication. Today, all systems tightly couple the optimizer placement to their corresponding experts. We break this abstraction. With SYMI, we decouple expert and optimized placement. We allow experts to be dynamic, adaptively replicated proportional to their popularity, and at the same time, we allow the optimizer to remain fixed, static, during the course of training. And every expert's optimizer is uniformly sharded across all nodes in the system. With this design, we can have 0 extra data movement for every rebalancing. The optimizer remains fixed. And to rebalance model weights, we repurpose existing communication that happens during the optimizer pass. Let me walk the design of SYMI throughout one training iteration. So the input token comes into the router. Every token is assigned an expert. We aggregate those assignments and store the resulting expert popularity distribution for this particular iteration. We route every token accordingly to its corresponding expert, according to this existing iteration's expert placement. We synchronize the gradients, move the gradients to the optimizer. The optimizer updates and computes the next iteration's weights. And in the meantime, our expert placement scheduler has computed the placement for experts and the new replication degrees for the next iteration, given this iteration's popularity. It propagates this metadata across components in the system, and now the optimizer will send back weights according to this updated placement. So this has no extra data movement. On the top, we have a static baseline. On the bottom, we have SYMI. It doesn't matter how many times you shard the optimizer. The total amount of data communicated is exactly the same for both gradients and weights. And for expert rebalancing, we want to change an expert assignment. If I'm GPU X holding an expert, it doesn't matter if I'm receiving the weights of the previous assignment or a new assignment. The amount of total data communicated is still exactly the same. What changes, however, is locality. And here we have to pay a cost. So in the top example, that the optimizer is sharded, split in two, half of the model weights and gradients communicated is local communication via PCIe or CUDA memcopy if you keep the optimizer in HBM. And in our design, only 1/n is local communication. We formulate this extra cost And it turns out that it's not that bad, especially for deployments that use more than 1,000 nodes. This is in the order of 1%. And we also empirically find that this overhead is not noticeable. So to prove this, I'm continuing to our evaluation section. We are comparing SYMI against DeepSpeed, a static placement baseline that at the time of this evaluation was a state-of-the-art system, supports constant expert replication, and also against FlexMOE, which supports adaptive expert replication, but it binds experts with their corresponding optimizer. As a result, it has to pay the cost of moving the optimizer, and to amortize this cost, it rebalances experts infrequently, every 10, 50, and 100 iterations in different flavors in this evaluation section. And then we have SYMI that decouples optimizers to their experts and rebalances on every training iteration. I'm starting with the end-to-end result, total training time until we reach a target training loss. And we see that SYMI is able to outperform the baselines by 25 to 30%. And this is for very different reasons. And in the next slide, I will try to attack each reason independently. One reason is convergence, how many iterations you need to reach that training target. The other reason is iteration latency, system performance. You multiply the two, you get total end-to-end training time. Starting with convergence, it turns out that the more frequently you rebalance, the best the convergence. So SYMI is able to requires almost 29% fewer iterations than DeepSpeed to reach our training target loss. And the FlexMOE baselines, the more frequently they rebalance, the better their convergence. And this is because adaptive expert replication drops significantly less tokens. In this example, I'm plotting the percentage of tokens that survived, and we see that SYMI is able to drop significantly, massively less tokens than the static baselines. And the FlexMOE baselines actually have very low token drops for the iterations that they are rebalancing experts. But because the expert distribution is very dynamic, this is no longer a good proxy in the next few iterations, so they have to drop. And to illustrate the reason behind this, we have many different expert popularity distributions. Some are very spiky like this one. So in this plot, with the blue line, I'm showing the number of replicas in the system. For DeepSpeed, this is constant. And with the orange line, I'm showing the normalized expert popularity during training so that everything above the blue line is getting dropped. And here is how SYMI works. Because SYMI is able to rebalance experts on every iteration, we are able to very closely match the assigned replicas to the observed popularity, and as a result, are able to drop very few tokens. And for the last result, I will show some latency numbers. Here, SYMI with the yellow bars is able to have very close latency to DeepSpeed. Actually, it's even a little better, and this is because of various optimizations that we do that I invite you to take a look at the paper to check. And we see that FlexMOE, the baselines that were rebalancing very frequently and did great on convergence, do not have enough iterations to amortize this cost. For example, FlexMOE with 10 iterations has only 10 iterations to migrate the huge cost of moving around the optimizer, which is not enough, and as a result, the average iteration latency is more than 35% higher across our systems. So this has been my presentation. I presented SYMI, an adaptive expert replication system. This is a very complicated system, so I had to skip many details. Feel free to ask me any questions. Thank you very much.